The broadcast is now starting. All attendees are in listen-only mode.
Hello, good morning. How's everybody? I'm Sean, application engineer from CADVision SolidWorks. So today, as topic say, we're going to discuss about fatigue. Okay. So before we start, is everybody can hear me? Okay. If you cannot hear me, you can type in the chat place to acknowledge me, or you can click the little hand button. Okay, you will find in your panels. Okay, in case you have any question, you also can type in there also. So let's get started. Fatigue, we all know about fatigue. Sometimes we use some of the products or anything, it just suddenly failure. Sounds like it's happened in a sudden, and most people, I mean, when during the design, it's typically didn't pay too much attention for it. However, as a product designer concerns, the warranty of life is quite a big issue that we can provide confidence to our customer. So it's a quite important phenomena. Fatigue is in this our product design industries. So in every years, it's caused a lot of financial loss, time loss, dealing with this kind of fatigue. But nowadays, the principle of fatigue is well understood. Actually, it's a complex interaction of time, loading, and working environment. Okay, so for example, a bridge could have a fatigue period of a very long time. However, a bullet shooting from the gun can have a very short time. Okay, so and we have temperature, cold and hot, thermal expansion, thermal contraction, working environment. Okay, this is a more complex phenomena. Maybe a temperature cycle, chemical cycle, or even a moisture cycle, that sort of thing. So the same thing between all of them is that they are cyclic. They are a kind of cyclic loading that at this cyclic loading continues, the material property change with time, so that at certain point it could not resist the loading anymore and it fails. Okay. So this is the definition from ASTM, American Society of Testing and Material. The process of progressive localized permanent structure change occurring in a material subject to condition that produce fluctuating stress and strain at the same point that accumulate crack or complete fracture after number of fluctuation. This is how we define fatigue. Okay, so at the meantime, this is quite a long word. So meantime, I highlight some of the words. So the same principle will be applied in SolidWorks simulation. These are the keywords: progressive, localized, permanent, fluctuating, cracks or fracture. Okay. So we'll see how it forms now. So this is typically a cutting. What we see when a fatigue occur, a fatigue fracture occur. So at the beginning, we see a little scratching, little micro cracks. Usually this is from metals, right? For some other materials, plastic, there might be the crack is, sorry, for example, like the concrete, the crack might be formed inside not in the surface, but anyway, let's talk about metal first. So the micro cracks, after the repeating cycles, we form quite a lot of surface crack on the surface, and what happens is they start to extend in the middle. We call it racket marks, and after a period of time again, suddenly they combine together, and we have this kind of pitch mark, some sort of wave forming things along the things, and this at this stage the crack grow faster and faster, and finally we see something that is not really nice to see. That is a final fracture region. This is typically the last section where the part is fractal. So we see some sort of coarse surface on there. Okay, actually, as we can see from this crack formation illustration, we can see that fatigue actually is a very long process. In not necessarily the last loading that creates the fracture, but actually the accumulative of the load along the usage of the product. So this could actually prevent if we do some analysis on the part at the beginning, so we can find out where is the origin of the fatigue point. We can take some issue on that. Either we do some heat treatment or we change the design. Anything we can do just to make sure that the first initial surface crack does not happen. Okay. So actually the fatigue, the theory is quite been well formalized. There's a German scientist called August Wöhler that first raised the theories of fatigue. So since now we're still using his approach to tackle a few things, so he raised up stress life approach. So it basically means that the stress that we facing in the product is directly linked with life, right? And then we also have strain life approach. It correlates the strain to the life of the product. And then we also have, this is quite a more modern one, it's called a linear elastic fracture mechanism. Okay. So here is some helpful tips for running a fatigue study in simulation and also in real practice. So for failure because of fatigue is the most common form of mechanical failure. So fatigue as a good practice should be included in the design process to give confidence on product warranty, and simulation should be backed up with the use of physical testing whenever possible. This is especially for the first few stage, which I will explain later about the factors that would affect fatigues. Okay, so don't rely on the fatigue factors alone when you come to fatigues. So it means that safety factors is what we typically the words we use in linear study. We have the safety factor plot. Okay, it's used in a linear static study, which we try to determine whether under a single loading is the region U. So this actually means that when we're talking about fatigue, basically we have to see both of them together, either whether under single loading is it U, or under a period of time that is fatigue, is it U. Okay. So here we come to see what kind of loading that we support to get in SolidWorks simulation. The first one is a constant amplitude on the left hand side, where we see a sine cosine wave kind of loading and unloading, or even reverse loading and compression, so forth and so forth. And on the other side, there is quite a more random curve where we call that variable amplitude. So in this presentation, we will briefly go through two of them. So here is a constant amplitude stress, cosine stress. So how do we determine the things? We call the things in the middle a mean stress, and we define this the lower peak of the curve as a minimum stress. and correspondingly the highest peak as a maximum stress. So the range we can say is maximum minus minimum, and we call this amplitude. So we can see that in the event that we in event model that we calculate, we always assume it is a mirror event in a constant amplitude stress. So they could be related into these two things. So if we have maximum minimum, we can get mean and amplitude. So this here comes to our loading events. In simulation fatigue study, we have different types of loading events. For example, we call zero-based reverse or fully reverse, denoted by R. When R equals to -1, we say it is a fully reverse. When R it is equal to 0, we say it is a zero-based. So it's quite straightforward. When we say the R is equal to -1, that means the mean is on the 0 line. So assumption that we have the mean coming down to this line. So basically the part is facing some sort of, if let's say it's a tension, the loading is tension, and then the test will be come back to compression. Tension and compression, tension and compression. If it is a zero base, okay, which means that the minimum is touching the 0 line, which means that if I have a loading, I will start from 0. I will start, if let's say it's a compression load, I will start compress and not compress, start compress, not compress, start compress and not compress. So basically this is a difference. So we can define more ratio, but this is the two classical events, load events, or we call loading ratios in our terms, simulation terms. In mechanical terms, we sometimes call the stress ratio. So let's have a look on the examples. So this is a trailer tow bar. It's used behind a trailer, a big track or anything. So typically we can see sometimes this little ball shaped times we can see in our car also, if you have installed one of them. Okay, so I hope we never use it. Okay, so okay, so this is actually is a customer case in the industry, automotive industry. So there's a standard we have to fulfill. We call ECR 5.5 in the sector 01. So this what we do is we have to do some fatigue tests according to the standard. So it's quite straightforward. What we say is we have a load of force around 6.5 kilonewton, okay, 15 degree at the tow ball around here, and the event should be defined as fully reverse. The part should be designed to last at least 2 million cycles. Okay, so how do we start first? Do we straight away go into fatigue? Not really. Usually what we start is we perform a linear static study first, and then we define a fatigue study. The thing we do a linear study first is that we have to make sure that the design is not yield at the first time first, because if it is yield at the first cycle, then it is not too much meaningful to perform cyclic study, as the performance could be very unpredictable. So we always go with linear study first. So this is what we do in linear study. So I believe you all have a clue on FEA study or you have attended a class elsewhere. So basically, this is what we do. First, we observe the symmetric conditions, so we could cut down the model into half to save time and mesh, that sort of things. And next thing is we have the hinge. Hinge joint, we define a hinge joint in the bolt hole. Okay. Then we have pin connectors at this region, a pin. And then we apply loadings according to the standard 15 degrees to the plane. Okay. And of course, as we do some mesh control over here. Okay. So this is the result we have. So typically we can see if you set it to 250, the overall will looks okay. Okay, but we do see some red spots over several places. I will show you. Okay, so these are the red spots. So if you do a factor of safety check of 1.4, this is the standard required 1.4. So we can see that overall is quite okay. However, we have some stress concentration area. So there is 3 very high area where we can see. So we have to determine whether this is a mathematically concentrate or it is because of our structural. Okay. So we look at the bolt hole. This is the hinge place where we set. So here, because we set boundary condition is hinge, the simulation is formed using the rigid bar. So from the shape and region, we can determine this is a false alarm because of the very line contact or that sort of thing creating the stress concentration. So here also we have a very sharp corner. Okay, so it could be due to the modeling error. We forgot to add feelers or anything. So because pressure is equal to force divided by area. So if the area is small, then it will be small. And then this area is supposed to be a load sharing area. So the area is very small. So that's why the pressure is very high also. So this could be a true alert. So this corner need to be paid attention. So how to verify that in FEA, this sort of stress concentration, how do we verify whether we need to pay attention or we do not need to pay attention? It's very easily done. We call it a convergent, okay, convergent study. So we just basically mesh more and more elements on that area. Okay, for example, in this area. So we mesh more and more, we can build out a table. So we see as the mesh going up, our stress value also going up. Okay, and then we use the stress value to plot a curve. The x-axis is DOF, the y-axis is the maximum stress. We can see the stress value actually going up, and it show a convergent behavior. So this is a place need to be attention. For the other 2 places, we probably will see singularity. That is, the curve actually diverging. It goes up to sky numbers when this mesh going smaller and smaller. So there's a false alarm. So here we need to pay attention on this. So since we already have this place already yield around, they converge around 550. So actually there's no need to continue to fatigue. So as the first cycle, the fatigue is for 1,000,000 of cycles, 1,000 of cycles, but at the first cycles, this part already yield. So there's really no point of going ahead before we make some design change. So typically we design this place for a more load sharing event, load sharing curvature, so that basically it could reduce the share. I mean, transfer some loadings towards other parts so that it reduces out. So on the same check, you see that it passed the check of 1.4. Okay. So when it's passed everything, the criteria is in linear static, so we can continue to fatigue. So linear static basically is a kind of guard a gut to decide whether we want to continue fatigue or not. So here comes how it took quite a while for us to go to fatigue. Okay, but here we go. A fatigue study. So it is inside here. This is quite an interface of fatigue. It's a separate module where we can define a fatigue study. Okay, so this is rather simple settings we can see compared to linear statics. There are only parameters, loadings, result options. Okay, so this is the loading is what we discussed just now about the loading events. Here we see the fully reversed, blah blah blah, how many cycles we want to determine, and what kind of study we are referring to. This study is referring to linear statics. So basically, a fatigue study is based on the previous study. Either it's a linear study, thermal stress, or non-linear study. Okay, basically we just based on the result of one cycle and with material property and determine what is the final fatigue result. Okay. So we have material over here. They are all steels. So typically for fatigue study, we need a curve that we call SN curve. Okay, so this is the SM curve. What we see SN curve is here. So this is the input where we put real numbers. Okay, so in probably in the study where we see we use logarithm numbers, or we do some testing. We have the logarithm numbers. So basically we do some conversion. So basically it's converting back from the logarithm, okay, back to the real state. So this is a very easy conversion. So I will not spend too many time. So just put in as much data point as possible. Usually at least 7, but just put as much as possible. Okay. So we just pick some important point and convert inside in a logarithm basis. Okay. So this is the stress ratio. This is what we say how we test the part, how we obtain the SM curve from real test. Okay, we define it here. And if the test data is not available, which is most likely the case, we can choose to derive from ASME curve. Either it's austenitic steel or it's carbon steel. So it will actually, what it do is based on the elastic modulus of the material and the current material and do some conversion based on the known curve. Okay, so for steel, it is still okay. For metal, it's fairly accurate. And for the others material, if fatigue is really a concern of the product design, and we will perform more and more similar tests in the future. So it is worthwhile to send the material to the lab and get an SM curve for a better correlate or a better result accuracy. So this is the material typically what we get under the under the experiment test. So this is this slide show some of the critical point that we have to take care of. Okay, so when the slope is changing, so this typical error we should have put in more data point for the better interpretation of the curve. Okay, so if let's say we define the starting point of the curve for 1000, and we define basically when our loading event should fall inside in this point. Okay, so typically at least we put 1000 for loading, and we put at here. So we can see this is what the curve we see is over here. Typically, this is the stress, the ultimate strength, the stress that the product can, the material, should I say, the material can handle. At the first cycle, is pretty high, and as the cycling going on, so please be reminded that this is a logarithmic scale. So actually, the cycle is very big. So it's going on that it will actually drop down and down and down, and until a point it becomes stabilized. Okay. So what we do is if we design the stress below here, okay, our overall product below here, theoretically it will last forever. Okay, theoretically it will last forever. However, because of some cost constraint or some manufacturing constraint, you will not end up here. Okay, so typically on this region, depends on standard or product usage. So we have a cycle we have here, let's say 20,000, then we have to consider that the maximum stress of our product size stay here. Okay, so this typically explains the event that ideally we wish to design over here that could last forever. Okay, so this shows how the fatigue calculator analysis. This is based on percentage, and here is based on logarithm. Okay, and we call this endurance limit. So this is a derived curve where we see this is derived using ASME carbon steel if the experimental test is not available. Okay, so this is the true result that the fatigue analysis will give us. One is the live plot, and the one is the damage plot. The live plot is typically how many cycles it will restrain before it yields or before it start forming cracks. Okay, so to be precise, we should define it as it start forming cracks rather than fatigue. So because in it's a real world, in the real world, the fracture is more to a random, or should we say a normal distribution random event. So here, what we say is it's likely that we have confidence that this place will crack this time. And for the damage plots, we can see where is the place that would damage. I mean, under the maximum life, where is the place that contribute the most damage? Okay. So compared to the last design, we see that although we have improved in the linear static study, okay, so we still have this place and this place not up to standard. So basically we need to refine this place. So it's quite interesting to see that it shows up quite well that where we want to improve. Okay, we are pulling, remember we are pulling this thing, so the load actually transferring throughout the place. So it could be this region, but with simulation tool we precisely analyze that what actually the area we need to be concerned. So this is on here we can see the changes we've made is we changed the radius of this, make more thickness, but we still make this slimmer. There's no need to improve here, but we improve here, and we slightly change the orientation a little bit over here. So everybody, so finally, all the things have passed through the factor of safety check. Okay, so this is the final factor of safety over here. Okay, so on here, as usual, if it is the same case that we actually not putting filters up anything, this could be a false alarm. So basically we focus on here. Okay, so both are safe. Okay, so this is the study property where we come from the fatigues. Actually, this is quite a big thing. So from this example once, we are computing the stress based on one Meissner stress, which is quite a good failure criteria for metals. Okay, for the others like stress intensity, or we say it's Tresca or maximum principle, it sometimes depends on different material. We will choose different, but for steel, 1 meters is quite good. Okay, and this is a different correction terms typically we use in fatigue. Currently, we support Goodman, Goebel, and SolidWorks. Okay, so from this case study, actually, I would like to raise some quite of important points. There is loading is separated into constant amplitude and variable amplitude. In the example one, we show constant amplitude. Okay? And the second point is try to use actual experiment fatigue data in design. Okay? If we have doing this kind of analysis time to time, it's worthwhile to invest on it. However, when it is not available, you can use approximate estimation, but take a note that we only pick on where the SN curve that is available inside SolidWorks, and we pick a curve that is close material properties, close materials behaviors. Okay, so lastly, you have to recognize that the mean stress might be different between the real test and the load case, and we require some correction methods which we will be discussed later. How to make it the result as close from theoretical world to practical world. Okay, so on the example 2, probably I will just go through a bit due to time constraint. We'll just go through variable attribute. So we can see what is a kind of variable attribute. So we can see from example 2, this is a good example of variable amplitude. Okay. So this is a part in the steering that is connected to expansion or anything. So we have some loadings. If we do some real tests, put some accelerometer over there. What we see is actually the load is quite random. Okay. However, we still can determine some of the peak load and bottom load. Some of the curve looks repeatable. So this is what we call variable amplitude events. So the method of converting the variable amplitude events into a usable simulation input is we call a rainbow flow method. Okay, so we will discuss this later. Let's have a look on the case first. So this is used in the material we use here is aluminum alloy, and we use the SN curve from military handbook. Okay, so here we have some connectors. Okay, the condition is and the other pin at this region, and the loadings is here. So it's 5,000 Newton along here. And this is the event response we collect during the test. This is varying. So we can identify where is the peak. So this is, we say this, we will choose this as our testing event. We assume it's repeatable. This could be some interference during the testing, but we'll choose this region. Okay, so this is the peak we have. So what we do is we use a characteristic. We call it rain flow counting method. So basically A is a peak, and this is compared to frequency. So basically it is peak to, you will see what we do is a up and down, up and down, up and down, up and down, up and down. Okay, so this is typically the characteristic of rain flow counting. Okay, so if you can get more up and down, it's more better. Okay, so we divide it as this. We can call, basically we can see it's a combination of cycles. So we can consider AD1 as a 1 cycles, BCB as a 1 cycle, EHE as a 1 cycle, GFG as a cycle. Okay, so I just put back the slide for you to check a while. So basically this is the conversion. So this is what we capture for a small portion of the event, and next one is what we convert back into the events. So here, here, and here, AD1 you can see is ADI. These are the very extreme cases, okay, which for the BCB is a more okay, it's not the extreme, but we still include it. It's called the rainfall counting method. Okay, so let's have a look. When we need to deal with this kind of events, typically on mobile wall file, vibration, or anything that random is, I mean, variable events, we have to tick this option. Okay, over here, where we first define a fatigue test. So here is same thing. It's quite simple. Under here, okay, we have the same thing we have in the event. So I think okay, and the next one is here. So the curve and the loadings is actually quite a little bit different than that. So let's see how we define the curve. Okay, so this is how we define the curve. Okay, so we just put in as small point as possible. So for your information, what we do is we actually can copy from Excel. So a better way to input so many curves is that we save the data, test data, everything into Excel, and we just copy over here. So over here we have different tree types. We have amplitude only. Okay, we have input sampling rate of amplitude. We can input time and amplitude also. Okay. Okay, so this is a view of the setup of the place, the materials, and the loading events. So quite simple compared to linear, just materials and events will quite do the job. Okay. This is the material properties we have. So this is a SM curve we have over here. This is a real data from the military handbooks. Okay. So in here is a metal, we choose for Mises. For the mean stress correction, we choose Kerbal. As for loading, so this is typically the beams for rainbow counting. This is what we talk about the rain flow countings. Okay, so actually when we input the whole test data, I mean for the loading data, the up and down random things, basically for simulation, for the theoretical that we develop for this kind of things, actually we will convert it into the beams. The beam is what we say is, let me just go back, it's actually this we call a beans and beans. Okay, 1 bean, 2 bean, 3 bean, 4 beans. So basically, it's up to us to adjust. So it's similar like mesh. This could go to kind of convergent also. The more beam we have, the more close that we are taking data from the rainbow cloudings. Okay, so we can say it's more accurate. However, this will affect the time to calculate, to solve the results. So we could take typically test it out on a well-developed product, and we find out what's the best bin number for different product. Basically, this is case-to-case things. Okay, we have to run a field study for the first time to find out what is the correct bin number for a product. Okay. So this is a loading. We already go through this. This is the loading, so we just check on this. So this is the bin number. Okay, so this is okay. This is the other factors that we're talking about. It's called reduction factor. This is a few factors that would make a difference between theoretical worlds and practical worlds. Okay, so the stress condition under vacuum and A could be different. The difference could be soft, could be little. Okay, in the vacuum state, we have we can say have a higher SN curve. In the air environment, we have a lower. Okay, so this even worse pre-shock. If we do some moisture test or anything, this could be lower. And if there's some chemical effects, that is even worse. Okay, so typically we have to correlate with the use environment and apply some reduction factors. Because what we use to determine the fatigue is actually from experiment. If we do some experiment that is, for example, under normal air conditions, so we get a fatigue curve. However, the application is used in some kind of moisture or chemical related environment. We can choose to input some factors to adjust our accuracy result. Okay, so again, this is kind of experiment things. Okay, for the first few times, but for one product, if the factors is already established, it could be said we can reuse that factor again for a similar environment. Okay, so this typically the factors we can that will affect our fatigues. So KC stands for corrosion, and we have KM, the loading modes, KF frequency, K1 size factor, KT temperature, KR reliability, KN notch effects, and KF fracting. So the top could be quite understandable. The bottom one, for example, size factor, reliability, notch effect, fletching, is more to kind of manufacturing things. For example, if we have a very tight quality control, then the size factor could be very close to 1. Okay, ideally everything could be close to 1. So if some of them have a negative effect, they will start reducing the life. They will be less than 1. Okay, so if let's say we have a bad control on on the tolerance, then the size factor could be low. Okay, we have not careful manufacturing process. For example, we can make some scratches. If there's some damage under transport, blah blah blah, then we have to adjust the effect correspondingly. Okay, so this is the finally how we accumulate fatigue strain reduction factor. Okay, so in this case we choose 0.61 using a reference. Okay. So on this case study, we see for a factor of 1, which means a very ideal case where we don't have any problems in manufacturing, every part is perfect. We have 128 blocks. The blocks means repeating effects. 128,000, sorry, blocks means repeat effects, repeat cycles. The curve that we input, the random cycles. However, what we have here is bottom. If we add, considering the practical factors, the factors that we have discussed just now, we can see we have a lower cycles. Okay, so somebody might ask, how do we actually calculate the factors? Basically, it's quite a quite a difficult task, quite a research task for you to build from scratch. But we could start by using some reference. So in some standards or some research paper, basically they will suggest that some kind of factors that we should adjust in, and then based on your product, we can adjust it time to time to make it more suited to your product. So for this automata, we choose 0.69, which is commonly used in industry. Okay, so this is typically what we have in the rainbow chart. Apart from the other result, this is the result we can have. So since the input is somewhat we call is kind of statistic, so the output is kind of statistics also. So if let's say we have this is a high stress event, if we have more of the high stress event, so what is the corresponding lifetime of these issues count. Okay, so as we are close to the end of presentation, so this is the summaries for example 2, variable amplitude events. So we got more points here, 4 points now. Okay, so the first is we have to try to obtain accurate service load history. Okay, and the second thing is remember the importance of notches in design, and try to provide the smooth stress gradient by designing a streamlined features. Okay, so and then we also be aware of there's many factors that can improve the resistance of corrosion fatigues. Okay, this is correspond to the factors, I mean chemical or that sort of things. Try to I mean, if that things happen, this is some of the action that we could take to adjust the factor as high as possible, such as shot pinning, coating, cladding, painting, chemicals, layers. Okay, to show that. So and then the last thing is don't ignore data scatter in fatigue testing. Okay, and the load data can result in significant variation in predicting lifetime. Okay, because as you can see, what we mean scatter is kind of scattering. It's like used typically because of in the SN curve we have the x-axis is kind of a logarithm scale. So if let's say we use we interpolate a smooth curve for a linear, okay, sometimes if for the test data the scatter is big, or should I mean that the variation between the point is big, the correlation factor to build a SM curve is low, okay, or we can say the error is big, then that it could possibly change the result quite much. So this has to be taken into a very careful account. So if a fatigue test, they have a lot of data scatter, there might be some testing is not precise, okay, or it's very difficult to test, we have to adjust the testing method, that sort of things. Or in case that the data is really scattered, we always consider the worst case. Okay, so this is quite important. Okay, So as a conclusion, okay, let's make a brief conclusion for the whole presentation. We have discussed that a common failure mechanism that is fatigue, and we discussed the August approach, which is the stress-related life approach, SN approach in simulation. And we have talked about different kind of events, either it's a constant or it's a variable events. Okay, and from these two examples, I've shared with you 7 assumptions. So the points, actually, the 3 points in example 1 and 4 points in example 2, basically is developed into assumption that we need to list out in our simulation reports. And for the last time is verify with feasible testing. Okay, so this is the end of the presentation. So if you have any questions, you could type here, or you could speak through your headphone. Okay. So I think I'm clicking to allow all the attendees to speak. So, yep. So any questions? So if there is no questions, then thank you for joining this webinar, and we shall see you soon on the next simulation webinar. Okay, see you. Bye.